Below, in this lecture, we will find out the area of the green triangle. In the drawing, we have a quarter circle. A or B is a quarter circle. Inside the quarter circle, we have line segment PQ that is equal to 3 units. Line segment AQ equals to 5 units in its length. This angle APQ equals to 90 degrees. And our mission is to find out the area of the green right triangle AOQ. So first of all, we focus on the right triangle APQ. And again, we focus on the right yellow triangle APQ, and we implement on this yellow right triangle the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right yellow triangle APQ is AQ, therefore the square of the hypotenuse is AQ square. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to PQ square plus AP square. Repeat again. In the right yellow triangle APQ, according to the Pythagoras theorem, here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, AQ square equals to PQ square plus AP square. AQ equals to 5 units in its length, therefore AQ square is 5 squared, that is 25, and it is equal to PQ square. PQ is 3, therefore PQ square is 3 squared, that is 9, plus AP square. AP is unknown, so we leave it as it is. In conclusion, we found out that according to the Pythagoras theorem, 25 equals to 9 plus AP square. We subtract 9 from this equation, and we get that 25 minus 9 is 16, equals to AP square. We take out all of this equation, and we get that AP equals to the square root of 16, that is 4. In conclusion, we found out that therefore side AP equals to 4 units. So I write it down in the drawing. Here AP equals to 4 units. Its length. Here, A or B is a quarter circle. You can easily complete the quarter circle to a circle, and then point O will be the center of the circle. Okay, if you complete the quarter circle to a circle, point O will be the center of the circle. And we have rule number 2 that states that a perpendicular from the center of the circle towards any chord bisects the chord. Okay, again, rule number 2. According to rule number 2, a perpendicular from the center of the circle towards any chord bisects the chord. Point O is the center of this circle. So if the center of the circle, that is to say from point O, we draw perpendicular on chord BC, here this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as M. So the perpendicular OM on on chord BC bisect chord BC. That is to say, it divides it into two halves. The first half is BM and the second half is MC. And of course, BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. In this case, the perpendicular OM bisects chord BC. That is to say, BM equals to MC. So we can implement rule number 4 in our drawing. From the center of this circle, that is to say from point O, we draw perpendicular on chord PA. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PA as N. And according to rule number 2, the perpendicular OM bisects chord PA. So we divide this into two halves. The first half is PM and the second half is MA. And because of the fact that PA in total equals to 4 units in its length, it means that the first half PM will be equal to 2 units, and the second half MA also will be equal to 2 units. We define the intersection point between line segment QA and perpendicular OM as N. We define angle PAQ, this angle is theta. So if you focus on the light yellow small triangle MNA, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees, that is the sum of the angles in any triangle. Likewise, according to the same rule, if you focus on the big yellow right triangle APQ, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Okay. In the next step, we will prove that the small right triangle AMN is similar to the big right triangle APQ. Okay. The big triangle APQ the big right triangle APQ is similar to the small right triangle AMN. So find those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle APQ in the big triangle equals to this angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. I repeat again. Angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, This angle, angle theta, is a common angle that belongs to both triangles. It belongs to the small triangle AMN, and it also belongs to the big triangle APQ. So we can write down that angle theta equals to itself. So we'll call angle theta two different names. Angle theta that belongs to the big triangle can be called as angle PAQ. Angle theta that belongs also to the small triangle can be called angle AMAN. So we call two different names to the same angle, angle theta. Angle theta is a common angle that belongs to both triangles. So repeat again. You can call to angle theta angle PAQ, and you can see that it belongs to the big triangle, and you can call to angle theta also angle MAN. In this way, we show that angle theta also belongs to the small triangle. Both of those two angles, the different names for angle theta. So they are equal to angle theta. So it's a common angle. Angle theta equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle AQP, this angle, the big triangle, equals to this angle. It is actually angle ANM, the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeating again. Angle AQP in the big triangle equals to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we succeeded to prove that all the angles in the big triangle are correspondingly equal to all the angles in the small triangle. Therefore, we actually proved that those two triangles, triangle APQ and triangle AMN, are similar to each other according to angle similarity rule. I'll write it down. The big triangle APQ is similar. This is the sign of similar to the small triangle AMN according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all the triangles in one triangle are correspondingly equal to all the triangles in another triangle, then you actually proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that the two triangles, the two right triangles, are similar to each other, we will conclude that PA in the big triangle over MA in the small triangle PA over MA equals to PQ in the big triangle over MN in the small triangle and it is also equal to QA in the big triangle over NA in the small triangle. I'll repeat again. Because of the fact that the two right triangles are similar to each other, we can conclude from it that PA over MA equals to PQ over MN equals to QA over AN. PA is 4 over MA is 2, and it is equal to PQ is 3 over MN that is unknown. We will leave it as it is, and it is equal to QA is 5 over NA that is unknown. In conclusion, we found out that four over 2 equals to 3 over MN equals to 5 over AN. From this equation, we can derive that 4 over 2 equals to 3 over MN. We'll multiply this equation by Mn, and we'll get that here 4 over 2 is 2. So 2 times Mn equals to 3. We'll divide this equation by 2, and we'll get that Mn equals to 3 over 2. 3 over 2 is 1.5. So the length of line segment Mn is equal to 1.5 units. This line segment Mn equals to 1.5 units. And from the same equation, here, this equation, we will conclude that 4 over 2 equals to 5 over AN. Okay, so 4 over 2 equals to 5 over NA. 4 over 2 is 2, so 2 equals to 5 over NA. We'll multiply this equation by NA, and we get that 2 times NA equals to 5. We'll divide this equation by 2, and finally we'll get that NA equals to 5 over 2. 5 over 2 is 2.5. In conclusion, we found out that line segment NA equals to 2.5 units in its length. So I write it down in the drawing that line segment NA, this line segment NA equals to 2.5 units in its length. What is the length of line segment QN? From the drawing it is very easy to see that QN equals to QA minus NA. QA minus NA is QN. I write it down. QN equals to QA minus NA. I'll repeat again. Qn equals to QA minus NA. So Qn equals to QA is 5 units according to what is given us in the question. and we just write minus NA. We just write down found out that NA equals to 2.5 units. 5 minus 2.5 is 2.5. In conclusion, we found out that line segment QN equals to 2.5 units in its length. So I write it down in the drawing that QN equals to 2.5 units in its length. This line segment QN equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. I repeat again, any triangle can be blocked by a circle. Therefore, we'll block the right green triangle AQO by a circle. Repeat again, we'll block the right green triangle AQO by a circle. So I copy the right triangle AQO. In a new page, we will block it by a circle. So actually, this is the right green triangle AQO that I copied from the original drawing. Now we block this right triangle by a circle. Inside this circle, we have peripheral angle AOQ that is equal to 90 degrees. Again, peripheral angle, this peripheral angle AOQ equals to 90 degrees in its size. And we also have rule number 5 that states that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Again, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I repeat again, according to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. So we have here peripheral angle ABC that is equal to 90 degrees, therefore this peripheral angle must rest on the diameter. And AC is indeed the diameter of the circle. So we can implement rule number 5 in our drawing. Because of the fact that peripheral angle AOQ is equal to 90 degrees, therefore angle AOQ must rest on the diameter of the circle. That is to say, QA is the diameter of the circle. Okay, so QA is the diameter of the circle. I write it down. QA is the diameter of the circle. And we know that any diameter, the diameter of any circle equals to 2 times the radius. So the diameter of this circle is equal to 2 times r, that is 2 times the radius. It is given as the equation that QA equals to 5 units in its length. So from this equation, we derive that 5 equals to 2r. We divide this equation by 2 and finally we will get that r equals to 5 over 2, that is 2.5 units. So the radius of this circle equals to 2.5 units. In the next step, I will copy point N from the original drawing to our drawing. Here, repeat again that this is triangle AQO. Okay? And this is also triangle AQO. So I can copy point N from triangle AQO from the original drawing to triangle AQO in this drawing. So this will be point N. We have already found out that AN equals to 2.5 units in its length. And we also found out that Qn is also equals to 2.5 units here. Qn equals to 2.5 units. We actually found out that QA is the diameter of the circle. On QA, that is the diameter of the circle, we have line segment QN that is equal to 2.5. But the radius also equals to 2.5. Therefore, QN must be the radius of the circle. Likewise, NA is located on the diameter of the circle. On QA, that is the diameter of the circle, and it is equal to 2.5. But the radius of the circle also equals to 2.5. Therefore, NA must be the radius of the circle. And we also know that the center of any circle is located in the middle of the diameter. So it means that QA, that is the diameter, the center of the circle will be located in the middle of QA. What is the middle of QA? Here, QA in total equals to 2.5 plus 2.5, that is 5 units. So the middle of the diameter is at point N. Okay, here. 1/2 is 1/2 of the diameter is QN, that is 2.5 units, and the second half is NA, that is 2.5 units, and therefore the middle of the diameter is at point N. And we also can say that the middle, the diameter of any, the center of any circle is located between the touching point of the two radii. And the touching point of those two radii is at point N. Okay, anyway, you actually can conclude that N is the diameter of the circle. And point N is the center of the circle. Point N is the center of the circle because it is in the middle of the diameter, and it is also the touching point of the two radii. Point N is the center of the circle. The next step, we join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is a point on the circle itself. That is exactly the definition of a radius. So NO is the radius of the circle, that is equal to 2.5 units. You can write down here that line segment NO equals, it is the radius of the circle, and it is equal to 2.5 units in its length. In the next step, I will copy the right triangle AMO, this right triangle, in a new page, and we will implement on this right triangle AMO the Pythagoras theorem. Side AM equals to 2 units in its length. What is the length of side MO, triangle AMO? From the drawing it is already to see that MO equals to MN plus NO. Again, MO equals to MN plus NO. MN is 1.5, NO is 2.5. So in total MO equals to 1.5 plus 2.5, that is 4 units. So MO equals to 4 units in its length. So actually, this is the right triangle AMO that I call it from the original drawing. Here by PT, in the relation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the sides of the perpendicular. The hypotenuse is OA, the square of the hypotenuse is OA squared, and it must be equal to the sum of the sides of the perpendiculars, that is to say, it must be equal to MA squared plus MO squared. OA squared equals to MA squared. MA is 2, therefore MA squared is 2 squared, that is 4, plus MO squared. MO is 4, therefore MO squared is 4 squared, that is 16. So in conclusion, found out that OA squared equals to 4 plus 16 is 20. So here we take out of this equation, and finally we found out that OA equals to the square root of 20 units in its length. So I'll write it down in the original drawing, that OA equals to the square root of 20 units. Yeah. OA equals to the square root of 20 units. In the next step, I will copy the right grand triangle AOQ in a new page, and we'll implement on this right grand triangle AOQ the Pythagoras theorem. AO equals to the square root of 20 units. AQ equals to 5 units. So actually, this is the right grand triangle AOQ that I call it from the original drawing. Here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, AQ squared, the square of the hypotenuse, equals to AO squared plus QO squared. AQ equals to 5, therefore AQ squared is 5 squared, that is 25. And is equal to AO squared. AO is square root of 20, therefore AO squared is square root of 20 squared, that is 20, plus QO squared. Here we subtract from this equation 20, and we get that 25 times 20 is 5, 5 equals to QO squared. We'll take out of this equation. And finally, we will find out that QO equals to the square root of 5 units. Okay. So I write down in the original drawing that QO equals to the square root, this QO equals to the square root of 5 units. Now it is very easy to find out the area of this green right triangle AOQ. Here, the square brackets is the sign for the area. It means the area of triangle AOQ equals to the area of any triangle equals to the base of the triangle times the height to the base. The height to the base must create 90 degrees with the base over 2. So, the base of the triangle AOQ is QO. The height is AO. Why the height is AO? Because it creates 90 degrees with the base QO. Here, this thing equals to 90 degrees. So 9 times AO over 2. I'll repeat again. The base of the right rectangle AOQ is QO. The height is AO, all divided by 2. QO equals to the square root of 5 units times AO equals to the square root of 20 units all divided by 2. So here we have the algebraic identity that states that square root of A times square root of B equals to the square root of A times B. According to this algebraic identity, we get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 all divided by 2. 5 times 20, 5 times 20 equals to 100, so inside the root we left with 100 divided by 2. The square root of 100 is 10 and 10 over 2 is 5. So in conclusion, we found out that the area of the green right triangle AOQ is equal to 5 square units. I repeat again, the area of this green triangle AOQ equals to 5 square units. In the next step, I will summarize the lecture. So, in this question, we found out the area of the green right triangle AOQ, this right green triangle. It's given us the question that PQ, this line segment equals to 3 units in its length, line segment AQ equals to 5 units in its length, and this angle APQ equals to 90 degrees. Again, our mission is to find out the area of this green right triangle AQO. So, we focused on the right yellow triangle APQ and we implemented in this right yellow triangle the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AQ, therefore the square of the hypotenuse is AQ squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to PQ squared plus PA squared. Repeat again. According to the Pythagoras theorem, in the right yellow triangle APQ, AQ square equals to PQ square plus AP square. AQ equals to 5, therefore AQ square is 5 square, that is 25, plus PQ square. PQ equals to 3, therefore PQ square is 3 square, that is 9, plus AP square. AP is unknown. So 25 equals to 9 plus AP square. We subtracted 9 from this equation and found out that 25 minus 9 is 16. So 16 equals to AP squared. We took out of this expression and finally found out that AJ equals to the square root of 16, that is 4. Here, line segment AP equals to 4 units in its length. Okay, in the next step, actually here we have a quarter circle, ABO is a quarter circle, and we can easily complete the quarter circle to a circle, and then point O will be the center of the circle. And you have the rule that if you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. I repeat again, rule number 4. A perpendicular from the center of a circle towards any chord bisect the chord. So here, point O is the center of the circle. So if from the center of the circle, that is to say from point O, we draw perpendicular on chord BC. Here this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as M. So here the perpendicular OM, according to rule number 2, bisects chord BC. That is to say, it divides into two halves. The first half is BM and the second half is MC. And of course BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. In this case, the perpendicular OM to chord BC bisects chord BC. That is to say BM equals to MC. We actually can implement rule number 2 in our drawing. In our drawing, we will draw perpendicular from the center of the circle, that is to say from point O towards chord PA. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O, OM and PA as M, and here the perpendicular OM bisects chord PA. So it divides it into two halves. Because of the fact that PA equals to 4 units, it means that the first half PM will be equal to 2 and the second half MA will be also equal to 2. This is according to rule number 2. In the next step, we define the intersection point between perpendicular OM and line segment QA as N. We define this angle as theta. So if we focus on the small yellow right triangle AMN, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees. And 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big triangle, the big right angle triangle APQ, this triangle, we have inside the triangle APQ, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Then we proved that the small right triangle AMN is similar to the big right triangle APQ. Okay, so why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. I repeat again, angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle equals to theta. It is a common angle that belongs to both triangles, as you can see here. Therefore, angle theta equals to itself. So we call to angle theta two different names. To emphasize that this angle equals to this angle belongs to both triangles. So if you relate to the big triangle, in the big triangle, angle theta is angle PAQ, and it is equal to Angle theta itself, if you focus on the small triangle, in the small triangle, angle theta is actually angle MAN. So actually angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. I'll repeat again. Angle AQP in the big triangle equals to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually we succeeded to prove that all three angles in the big triangle, big right yellow triangle, are correspondingly equal to all the three angles in the small yellow right triangle AMN. Therefore we actually proved that the two right triangles are similar to each other according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually proved that the two right triangles are similar to each other according to angle similarity rule. From the fact that the two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. Repeat again. PQ over MA equals to PA over MA equals to PQ over MN equals to QA over AN. PA equals to 4. MA equals to 2. So PA over MA is 4 over 2. PQ is 3. MN is unknown. QA is 5 over AN. Okay? So from this equation, we will derive that 4 over 2 equals to 3 over MN. 4 over 2 equals to 3 over MN. We multiplied this equation by MN. 4 over 2 is 2. Then we multiply this equation by MN. And we got that 2 times MN equals to 3. We divided this equation by 2 and finally we found out that Mn equals to 3 over 2, that is 1.5. This line segment Mn equals to 1.5 units in its length. So from the same equation, this equation, we derive that 4 over 2 equals to 5 over Na. Again, 4 over 2 equals to 5 over Na. 4 over 2 equals to 5 over An. 4 over 2 is 2 and is equal to 5 over An. We multiply this equation by An and finally we found out that 2 times An equals to 5. We divided this equation by 2 and finally we found out that An equals to 5 over 2. 5 over 2 is 2.5. So in conclusion we found out that this line segment An equals to 2.5 units in its length. What is the length of line segment Qn? From the drawing it is very easy to see that the length of Qn is Qa minus Na. Again, Qa minus Na equals to Qn. I repeat again. Qn equals to Qa minus Na. Qa equals to 5 units. We just right now found out that Na equals to 2.5. Therefore, in total, Qn equals to 5 minus 2.5, that is 2.5. In conclusion, we found out that line segment Qn equals to 2.5 units in its length. Then, we know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, I copied the right triangle A or Q in a new page and we blocked this right triangle by a circle. So this is the right green triangle AQN, AOQ, AOQ, the copy from the original drawing, and we block this triangle by this circle. Inside this circle, we have peripheral angle AOQ that is equal to 90 degrees. This peripheral angle AOQ equals to 90 degrees. And we have rule number 5 that states that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Here, rule number 5 says that any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here, peripheral angle ABC, this angle equals to 90 degrees, therefore it must rest on the diameter of the circle, and here indeed AC is the diameter of the circle. So we can implement rule number 5 in our drawing. In our drawing, peripheral angle AOQ equals to 90 degrees. This angle, therefore peripheral angle AOQ rests on the diameter of the circle. That is to say, AQ is the diameter of the circle according to rule number 5. AQ or QA. So QA is the diameter of the circle. We know that any diameter of any circle is 2 times the radius. So the diameter of this circle QA equals to 2 times the radius. That is to say 2r. From one side, but from the other side, we know it is given us the equation that QA equals to 5. And from this equation, we derive that 5 equals to 2r. We divided this equation by 2 and finally found out that r equals to 5 over 2 is 2.5. The radius of this circle equals to 2.5 in its length. Okay, now I copied point N from the original drawing, this point, to our drawing. This is triangle AQO, and this is also triangle AQO. Therefore, I can copy point N that is on the hypotenuse of this green right triangle AQO to this the same right triangle AQO. So I copied point N from the hypotenuse AQ to here, the same hypotenuse AQ here. So this is point N that I copied from the original drawing. So here we have line segment AN equals to 2.5 and line segment NQ also equals to 2.5. Okay, we know that QA is the diameter of the circle, and the center of any diameter is in the middle of the diameter. The QA equals to 5 units. Therefore, the middle of the diameter will be at point that is 5 over 2, that is 2.5. Here, Qn equals to 2.5, An equals to 2.5, therefore point N is the center of the circle, the center of the diameter, that is also the center of the circle. Or we can say also that because of the fact that An equals to 2.5 and the radius also equals to 2.5, An that is located on the diameter and it is equal to 2.5 must be the radius of the circle. Likewise, line segment NQ equals to 2.5, it is located on the diameter, but the radius also equals to 2.5, therefore NQ must be the radius of this circle. And we know that the touching point between the two radii in any diameter, it is the center of the circle. Where is the touching point of those two radii? Here, at point N. Therefore, point N must be the center of the circle. Here, point N is the center of the circle. Then we join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point on the circle itself. This is exactly the definition of a radius. Therefore, NO is the radius of this circle, that is equal to 2.5 units. Here, NO equals to 2.5 units. It's left, it is the radius of the circle. In the next step, I copied the right triangle AMO in a new page, and we implemented in this right triangle AMO the Pythagoras theorem. The length of side AM is 2 units. Side MO, it is very easy to see from the drawing that MO equals to MN plus NO. So MO equals to MN, that is 1.5, plus NO, that is 2.5. In total, MO equals to 1.5 plus 2.5, that is 4 units. Here, MO equals to 4 units. This is the right triangle AMO that I copied from the original drawing. MO equals to 4 units. In its length, AM equals to 2 units. Now we implemented here the Pythagoras theorem. According to the Pythagoras theorem, AO square equals to MA square plus MO square. So OA square equals to MA square. MA is 2, therefore MA square is 2 squared, that is 4, plus MO square. MO is 4, therefore MO square is 16. 4 squared, that is 16. So OA square equals to 4 plus 16, that is 20. We took out of this equation and found out finally that OA equals to the square root of 20 units. Yeah, OA equals to square root of 20 units. Then I copied the right triangle AQO for this original drawing and we implemented on this right triangle AOQ, the Pythagoras theorem. Side AO equals to the square root of 20 units. The hypotenuse AQ equals to 5 units. This is the right triangle AQO that I copied from the original drawing. According to the Pythagoras theorem, AQ square equals to AO square plus QO square. So AQ is 5, therefore AQ square is 5 square, that is 25. It is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 square, that is 20, plus QO square. We subtracted 20 from this equation and we found out that 25 minus 20 is 5. So 5 equals to QO square. We took out of this equation and found out finally that QO equals to the square root of 5 units. Here, QO equals to the square root of 5 units. QO equals to the square root of 5 units. Now it is very easy to find out the area of this green right triangle AQO. Here, the square bracket is the sign for the area. The area of any triangle is the base of the triangle times the height to the base over 2. The height must get 90 degrees with the base. The base is QO. The height is AO because it creates 90 degrees with the base QO. Okay, so it is QO times AO over 2. QO is equal to 5 units. AO is equal to 20 units, all divided by 2. We have the algebraic identity that square root of A times square root of B is equals to the square root of A times B. Therefore, the square root of 5 times square root of 20 is the square root of 5 times 20 over 2. 5 times 20 is 100. So inside the root we have 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. In conclusion, found out that the area of this grand right triangle AQO equals to 5 square units. Okay, I repeat again, the area of this right grand triangle AQO equals to 5 square units. Okay, thank you very much.